Hello guys, welcome to PLC Goods video tutorial. In this video we are going to learn what math instructions are. RSLogix 5000 categorizes them into basic math instructions, advanced math instructions, trigonometric functions, math conversions, and compare instructions. I will explain them briefly. Also, I will show you how the help window of the RSLogix 5000 can help us learn each instruction. Then I will use these instructions to do a simple project to fill and drain a water tank system. I created a virtual processor using RSLogix Emulate 5000. Also, I use RSLinks to connect the virtual processor to RSLogix 5000. Furthermore, I configured the virtual PLC station in RSLogix 5000. Now let's look at the basic math instructions. This instruction computes a mathematical expression like these, where a and b can be either integer or real numbers. Addition, subtraction, multiplication, and division are the next basic math instructions that get two tags or numbers to calculate a desired value. The module instruction divides source A by source B and stores the remainder in the destination address. For instance, if source A and source B are equal to 12 and 5 respectively, the answer is 2. A square root, negate, and absolute value are the other basic math instructions that get only one number. Let's use the division instruction to learn how we can use a basic math instruction. First, I should determine what source A and source B are. Here I can enter a constant number or a tag that includes a number. Also, I should determine where the result should be saved. Note that I need to determine the data type of the entered tags. Usually we use a double integer or a real format to store numbers. Currently, I prefer to use a double integer data. Similarly, for the next division, let's use A and B tags, but I want to store its result in another address with a different data type. Here, let's select a real data type instead of double integer to show you an important point of using math instructions. Let's verify the project and download the program to a virtual PLC. Now let me open the program tags table. Click on monitor tags to change and see the tags values. Let's see the result of two division instructions. Note that we cannot divide a number by 0, which is undefined. Let me change the second tag from 0 to 1. Now we can see the correct answers for both division instructions. Let's change the second tag value. Now there are two different results, 2 and 2.5. Because in the first division, the data type of this tag is double integer. This data type can only store integer numbers, so 0.5 is omitted from the correct answer. But in the next division, the data type of this tag, des2, is real. It can store floating point numbers as well as 2.5. Note that I cannot change the stored number by tag B to 2.5 because its data type is double integer. So when you are using math instructions, pay attention to data type and some conditions which can cause wrong results. Now let me delete the division instructions and explain how a compute instruction works. Let me open the help window of RSLogix 5000. Here you can see its contents and search for the desired topic. Let me write the compute instruction name, which is CPT. The help window helps us to learn instructions to use in our programs. Here we can see which data type we can use for compute instructions, which are short integer, double integer, and real numbers. As I mentioned before, this instruction can be used to calculate mathematical expressions. Here we can see some examples to learn how this instruction can be used. This table shows the operations and their order which can be used to write a mathematical expression. Note that the operations you write into a mathematical expression are performed in a recommended order, not necessarily the order you write them. You can override the order of operation by grouping terms within parentheses. Here we can see some trigonometric functions and advanced math operands and other basic operands like this. Two multiplication signs in a mathematical expression means to the power of. For instance, the value of 5 to the power of 3 is 125. Now let's see what the len operand is. The natural logarithm of a number is its logarithm to the base of the mathematical constant e. Now let me use that to write a mathematical expression. First, I need to determine where the result should be saved. Then I need to write my mathematical expression. The domain of the len function is the set of strictly positive real numbers, so the A tag must not include a negative number. Note that if you click on Advanced Math tab, you can view and insert a natural log function, the log and xpy instructions. Similarly, you can use these trigonometric functions, which are sine, cosine, tangent, and their inverse functions. Now let's insert a sine instruction. Assume we need to calculate the sine of 30 degrees and store its result on B tag. Note that trigonometric functions like the sine instruction work based on radian, which is a unit of angle. So I need to convert 30 degrees to its equivalent in radians. Now let's look at math conversion instructions. The DEG instruction converts its source value in radians to its equivalent value in degrees. The RAD instruction works inversely. It converts its source value in degrees to radians. We use the TOD and FRD instructions to convert a value to and from BCD. BCD, or binary coded decimal, is a representation of a number in which each decimal digit is encoded in binary with 4 bits per a decimal digit. This table shows some examples of decimal numbers and their equivalent BCD value. The TRN instruction removes the fractional part of its source value and stores the result in a destination address. Now let me use this instruction to convert 30 degrees to its equivalent value in radians and store the result in A tag to calculate its sine value with the next instruction. Let's test this program to calculate sine of 30 degrees. Obviously, the correct answer is 0.5. Pay attention. As I mentioned before, the data types of the defined tags are important. The data type of the A and B tags is double integer. This data type is only used for integer numbers, but when we are using trigonometric functions, we usually need to work with real numbers. The program calculated A and B tags incorrectly because the data type of the A tag is integer, which removes the fractional part of a real number. So let me modify the data type of the A and B tags and test the program again to see if I can get a correct answer. Okay, my program calculated the correct answer successfully. Until now, I explained the basic and advanced math instructions. Also, I tested a simple program using a trigonometric function and a conversion instruction. The other conversion instructions can be used similarly, and you can find and read their description and tips in the help window. Now let's see what the compare instructions are. Compare instructions are used to compare two values of the same data type. When the comparison is true, then it can activate a bit of memory or turn on a digital output. For instance, this instruction greater than or equal to tests whether source A is greater than or equal to source B or not. The other comparison instructions are less than or equal to, greater than, less than, not equal to, and equal to work similarly. The next three instructions, mask equal, limit test, and compare, are a little different. Let's learn them using the help window. First, let me type MEQ, which is a short form of the mask equal instruction. This instruction passes its source and it compares values through a mask and compares the results. But what is the meaning of mask in a PLC programming? Note that when you enter a number, RSLogix 5000 consider it as a decimal value. If you want to enter a number using another format like binary or hexadecimal formats, you will need to use a suitable prefix. Okay, this instruction gets three numbers, and here you can see an example of using the instruction. The second number is the mask number. 0 in the mask means the selected bit is blocked, and 1 means the selected bit can be passed. So if all these bits of the first and third numbers are equal together, this instruction sets the output light 1 to 1. Otherwise, this output is set off. For the first example, the selected bits by the mask are equal together. In consequence, the light 1 is on. Note that the first 4 bits are not used for the comparison. So, like the right example, if we change the first 4 bits, the output is remained 1. Now let's see what the limit instruction is. This instruction checks whether the test value is within the range of low limit or a high limit. For instance, here when the test value is a number between 0 and 100, the output light 1 will be on, otherwise it will be off. Let me explain the last instruction in this video, the compare instruction. This instruction performs a comparison on the arithmetic operations you specify in the expression field. Note that we can use these operations to write expressions. Note that we need to use a comparison operand at least. Let's write a simple program. Let me press Ctrl plus Z keys on my keyboard to start the programming steps with this program, which I tested already. I want to turn on a digital output when the sign A is less than 0.5. Let's verify the project and download the program to a virtual PLC. Obviously, the sine of 30 degrees is exactly equal to 0.5. So this comparison is not true and my output remains off. Now let's change the stored number in the A tag. For instance, let's test this program when the A tag is equal to 20 degrees. Since sine of 20 degrees is less than 0.5, my program has turned on the output. Now let's use these instructions to do a simple project. First, let me introduce the tank system in Factory I/O and test the final project to see its performance. Then I will show you how this plant can be designed in Factory I/O and its PLC program can be written in RSLogix 5000. This tank has two valves for filling and discharging. These valves are controlled by a voltage from 0 to 10 volts. Here we also have a level meter. This sensor sends a voltage between 0 and 10 volts to my controller when the water level is between 0 and 300 centimeters. Note that in this project I use my virtual inputs/outputs in Factory I/O, like this control box to control the water tank system. I won't use the real switches and push buttons which are connected to my PLC. I can use this potentiometer to determine my desired water level from 10 to 290 centimeters. You can see that on the first digital display. You can view the current water level on the next digital display. The water level can be a number between 0 and 300 centimeters. If I press the start push button and the water level is less than the desired level, the controller should open the filling valve until the water level reaches the desired level. The level meter signal should be used to compute and to display the current water level on this digital display. Also, I can use this potentiometer to discharge the tank manually. Now let's raise the desired level. The controller opened the filling valve to raise the water level automatically. Note that I can stop the filling process by either emergency or the stop push button. Let me show you how you can design this water tank system in Factory I/O. After that, I will write a PLC program to control a water level. From the right list, insert the tank. This tank supports two modes, analog and digital. Let's select the digital mode. Note that industrial equipment can be categorized into two groups, actuators and sensors. Actuators can be connected to a PLC's output and sensors to its inputs. If I click here, I can see my actuators' names. When the digital mode is selected for the water tank system, it has only two digital actuators, filling and discharging valves. Let's test the filling valve. Note that we can control the equipment manually. If we want to use a PLC to control the equipment, the no failure mode should be selected for the equipment. Injecting an on failure and injecting an off failure modes are used to simulate the conditions that the selected equipment is defective. By default, I select the no failure mode. Similarly, let me test the discharging valve. In this project, I need more equipment such as a level meter. So let's change the selected mode for the water tank to analog mode. In this mode, the filling and discharging valves are controlled by a voltage from 0 to 10 volts. In this mode, I can determine how much the two valves should be open. Also, I can use this analog level meter. This sensor sends a voltage from 0 to 10 volts to my PLC when the water level is changing from 0 to 300 centimeters. Now let's design a control box. You can insert the necessary equipment from the right list. I can press the V key on the keyboard and use my mouse to change the height of the equipment. Each push button has an internal signal light and two tags, a tag for the push button and a tag for its internal light. Now I can see the tag of the start push button's light. I need to click on the sensor's tags icon to see and change the selected tag for the push buttons. The start push button is normally open, but the emergency and stop push buttons are normally closed. Now let's define suitable tags for the two potentiometers. This potentiometer can send the real number to my controller. You can assume it is a voltage. For the first potentiometer, I will use math instructions to change its range to a number between 10 and 290 as my desired water level. Also, I will send the selected level to the first digital display. I select an integer format for the two digital displays to show my desired level and the current level. Note that Factory I/O selects the default tag for each piece of equipment if I change its mode. So let me modify the tags of the two digital displays again. Okay, I inserted my equipment. Now I should connect them to my controller. So let me click on drivers to determine my controller type. In the configuration window, I need to write the IP address of my PLC station and the slot number of my CPU module. Then I should define some suitable tags. These tags will be shared between my controller and Factory I/O. In this project, I need three digital inputs to use the emergency and start and stop push buttons. I don't need any digital output, but I need three analog inputs because of the level sensor and the two potentiometers. Note that the tank has two analog valves which should be controlled by my PLC. Finally, I need two tags whose data type is integer to display the desired and current levels on the two digital displays. Now let's connect the equipment to the defined tags. I forgot to modify the tag of my first potentiometer. Let's select it and define a suitable tag for the first potentiometer. Now let me connect Factory I/O to my controller. Factory I/O has connected to my controller successfully, but it has not detected any tags in my PLC because I have not defined these tags in my PLC yet. So let's launch RSLogix 5000 to define and use the tags. I already configured my hardware. Now let's start the programming steps. Although my final program to control the water level is simple and short, I will show you how a PLC program can be divided into three subprograms. This method is very useful to write long and complex programs for several systems. Up until now, we were writing our programs inside the main routine which belongs to the main program folder. I can right-click on the main task and create another program folder beside a main program folder. In the current project, a part of my program uses the first digital display to show the desired water level. So let's write desired level as the name of the new program folder. Here I can write a description. Then I can determine when a new program folder should be executed. When my controller detects a fault, when the main task folder is executing cyclically, or when a PLC is powered on. Let's create a new program folder under the main task beside the main program. Similarly, let's create another program folder to use the level meter signal to calculate and to display the current water level. Each created folder has a program tags table by default. I need to create a new routine in which I can write my program there. After writing a name and a description for the new routine, I can select my programming language. We are using ladder diagram language. The next field determines where the new routine should be created. Here I have three programs folders. I can specify the executing order of these program folders. Now PLC executes the main program folder first, then the desired level, and after that the real level folder. PLC continues this cycle until we stop it. Each program folder has its own program tags table. We cannot use a tag defined inside the program folder in another program folder. If we need a tag that can be used in all program folders and also can be shared with Factory I/O, we should create it in the controller tags table, like these inputs, outputs, addresses of my PLC station. Let's define these tags which I used in Factory I/O. We should select a suitable data type according to the selected data type in Factory I/O. I use a description box to write the equipment name which is connected to the new tag. Similarly, we can define the other tags. I have two groups inside my controller tags table. The first one includes the new tags. I will use them as the virtual inputs, outputs of my controller. The next group includes the addresses of my real inputs, outputs. We can connect them to real actuators and sensors. Now let's open the main routine under the desired level folder to write a program. First, I insert a multiply instruction. Note that the first potentiometer, which is connected to this tag, is going to send a number between 0 and 10 to the controller. I can use this mathematical expression to convert that to a number between 10 and 290. Let's save the multiplication result in this tag. Note that I need this tag only in the current program folder. Now let's use an add instruction to add 10 to the previous result. Now let's send the result to the tag which is connected to the first digital display. So the current program converts the first potentiometer's voltage to a number between 10 and 290 and displays it on this digital display. Now let's create a new routine in the next program folder to write a program to use the level meter's voltage to calculate the current water level. Similarly, you can write your program inside each routine Now let me explain my final program. In this program folder, I only use this multiply instruction to convert the received signal from the level meter to a number between 0 and 300 centimeters. This is my program inside the main routine. First, I used latch and unlatch instructions to store a start and stop request on a bit of memory. At the third run, if I press the start push button and if the desired level is less than the current level, my program sends 0 volts to close the filling valve. Otherwise, if I press the start push button and the desired level is greater than the water level, my program sends 10 volts to open the filling valve. The second potentiometer sends a voltage between 0 and 10 to my controller. Also, the discharging valve works with a voltage from 0 to 10 volts. So based on the fourth round, if the start push button is pressed, my controller moves the received voltage from the second potentiometer to the discharging valve using a simple move instruction. Finally, in the last round, if we don't have any start request, in other words, if I press the emergency or stop push button, my program closes the two valves using two clear instructions. Note that if you click on the Move Logical tab, you can find the move and clear instructions. Now let's verify the project. Here are two warnings. I need to open the Program Properties window of these two program folders to select a main routine for the two new program folders. Note that a program folder starts its execution from its main routine. Okay, I wrote my final program in three program folders. All of them can use the defined tags or addresses in the controller tags table. Now let's download the project to the controller. Now let's reconnect Factory.io to the controller. At this time, Factory.io detected all these tags in my controller and I can test my program. Now we are going to learn the move logical group of instructions. We will start with the move and mask move instructions. Then we will learn logical bitwise instructions. Also, we will see what the swap, byte, clear, and bit filled distribute instructions are. Finally, we will do a simple project using these instructions to turn on 8 fans of 8 industrial cabinets. Let's explain the move logical group of instructions. The move instruction copies the source value to its destination address. This instruction does not change its source value. Now let's learn the mask move instruction. This instruction copies the source value to a destination address, but it uses a mask value to determine which bits of the source value should be copied. For instance, let's write A as the source value. I'll select the short integer format for its data type, which uses 8 bits to store numbers from -128 to 127. The A value should be copied to a destination address, but here we can determine which bits of its 8 bits should be copied. So let me enter the mask value in binary form. Based on the entered number, the MVM instruction copies only bit number 4 to 7 of tag A. If I want to use the MVM instruction like the move instruction, I should set the 8 bits to 1. Let's enter tag B as the destination address and select short integer as the data type of tag A and B. Now let me download the program to a virtual processor. Now let's open the program tags table to see the values of the A and B tags. Here I am entering some values in binary form, but RSLogix 5000 displays its value in decimal style. I can change the selected style in this column to see a number in its binary form. Based on this value, only bit numbers 4, 5, 6, and 7 of the A tag can be copied to B tag. Now let's open the help window and search for the MVM instruction. Here you can see a complete description of this instruction. Here is an example with double integer numbers. A double integer tag uses 32 bits to store numbers. In this example, these bits show the stored number in the destination address before enabling the MVM instruction. These bits are the source value and these bits belong to the mask value. Based on the mask number, the MVM instruction copies only these bits from the source value to the destination address. The last group of bits shows the state of the destination address after enabling the MVM instruction. Note that you can search for data types in the help window to see all data types and their properties. For instance, here we can see the range of short or double integer numbers. Also, we can select another data type to see its details like counter structure. Here we can see what happens if we save a real number on a tag whose data type is integer. Okay, after the move and mask move instructions, there are 4 instructions to perform bitwise logic operations. These instructions are bitwise AND, bitwise inclusive OR, bitwise exclusive OR, and bitwise NOT. Let's review basic logic with this simple program. Note that for activating or inactivating a bit of PLC memory, I can right-click on the bit of memory and select toggle bit, or just press Ctrl plus T on the keyboard. The first run performs AND logic between S1 and S2. Out1 is on if S1 and S2 are activated. The next run represents the OR logic. Out2 is on if S1 and S2 or both are activated. So if we want to turn off Out2, both S1 and S2 should be off. Run number 2 performs XOR logic between S1 and S2. So out3 will be on or true only when the state of S1 and S2 are not the same. Finally, run number 3 represents a NOT logic. If the state of S1 is true, out4 will be off. and if the state of S1 is false, out4 will be on. Now let's see how the bitwise XOR instruction works. When this instruction is enabled, it performs a bit-by-bit XOR operation between source A and source B and stores the result in the destination tag. Based on source A and source B values, B tag is equal to this value in binary form, which is equal to -61 in decimal form. Note that to see the result in binary form, we can use the program tags table. The next instruction is swap byte. This instruction rearranges the bytes of a value. First, let's see how this instruction works when we use that for a double integer number which includes 32 bits. Let's divide them into 4 groups: A, B, C, and D. Now if you want to rearrange the bytes to this pattern, I can use the swap byte instruction and select the reverse option for that. So based on the selected mode, the result will be a double integer 2 with this value. Note that this instruction has 3 order modes: reverse, word, and high-low. Here you can see an example of each order mode. After the swap byte instruction, the bitwise NOT instruction inverses the state of each bit in a specific address. The clear instruction clears all the bits of its destination address or tag. Now let me explain this instruction, the bit field distribute instruction. This instruction copies the specified bits from the source value, shifts the bits to a suitable position, and writes them into the destination address. This instruction gets 5 parameters. Let's learn how this instruction works using an example. When we enable this instruction, it copies a group of bits from the source value to the destination address. The group of bits is identified by the lowest bit number in the group and the number of bits lengths. The destination bit identifies a bit number in the destination address. So in this case, the BTD copies the selected bits on these bits of the destination address. Note that if the length of the bit field exceeds beyond the destination address, the instruction does not save the extra bits. Also, the source value remains unchanged. Okay, I explained the move logical instructions. Now let's define and do a simple project. Note that here I have a virtual input-output module which has 32 inputs and 32 outputs. Now let me define a project. Here you can see an industrial cabinet with a fan. I want to write a program to turn on off the fan. Usually there are some electrical devices inside the cabinet. Let's assume it has a door limit switch, a temperature sensor, and a start push button which have connected to a PLC with this diagram. In this project I use a virtual processor. When the cabinet door is closed, this switch is closed too, so the voltage reaches the PLC input module and the related input address is true in a PLC program. The temperature sensor is connected to the PLC using its normally closed contact. So when the temperature is higher than a specified temperature, for instance 30 degrees centigrade, This contact is open, so the voltage cannot reach the PLC input, and the related input address is 0 in my program when the temperature is higher than 30 degrees centigrade. Like the door limit switch, when I press this push button, the voltage reaches the PLC input and its related input address is true in a PLC program. This program can turn on the fan. Based on this program, when the temperature is higher than 30 degrees, the related input address is 0. So the state of this normally closed contact remains closed and it passes a virtual power in my program. When I press the push button, its related address is 1. So the state of this contact changes to closed and it can pass a virtual power in the program. Similarly, when the door is closed, this contact can pass a virtual power. Overall, if the temperature is higher than 30 degrees or the push button is pressed manually and at the same time the cabinet door is closed, the program turns on the fan. Note that I used both an OR and an AND logic in the program. Now suppose there are 8 cabinets and we need to turn on their fans based on the previous program logic. Naturally, we need 24 digital inputs for 8 limit switches, 8 temperature sensors, and 8 push buttons. Also, we need 8 digital outputs to turn on 8 fans. We can repeat the previous program 8 times, but let's write a PLC program using the move logical instructions. First, I use this bit field distribute instruction to move the first 8 digital inputs to the first 8 bits of a PLC memory. I use a tag with this name, limit switches, as the destination address. Its data type is double integer. This data type has 32 bits, but we only need its first 8 bits to store the state of 8 limit switches. Similarly, in the next run, I use another bit field distribute instruction to move the second 8 digital inputs to the first 8 bits of a PLC memory. These digital inputs are connected to the normally closed contact of the 8 temperature sensors. So I need a bitwise NOT instruction to inverse them. In the third run, let's use another bit field distribute instruction to move the third 8 digital inputs, bit numbers 16 to 23, to the first 8 bits of a PLC memory. Here I use a tag with this name, push buttons, as the destination address, because these bits represent the status of the 8 push buttons. Now I can use bitwise logic instruction to write a program to turn on off the 8 fans in one run. I need a bitwise inclusive OR and a bitwise AND instruction. Let's save the final result on this tag, variable 2. Note that I only need its first 8 bits to turn on the first 8 bits of the PLC outputs. So let's use a masked move instruction. Here I enter the mask value in hexadecimal form. Based on this number, the MVM instruction only transfers the first 8 bits of variable 2 to the output module, which can turn on off the 8 fans. Now let's download the program to a virtual controller. Let me open the program tags table. Also, I should change the controller mode to run mode. Note that in normal conditions, these inputs are activated by the temperature sensors. Obviously, the defined tags have 32 bits, but we need only the first 8 bits of them in this project. Suppose only the first 4 cabinet doors are closed, so the first 4 cabinet fans can be turned on if I activate their push buttons or inactivate their temperature sensors. The doors of the next 4 cabinets are open, so PLC cannot turn on their fans. Okay, this program can be extended to 32 cabinets easily. It only needs to modify the mask number in the program. Thanks so much for watching this video. See you in the next video.